All right, so in this new part, part 8, we're going to discuss the synthesizing the transfer function and the coupling matrix, not just in the omega equals 1, the normalized frequency domain, but in the real frequency domain that we want. There are essentially two main methodologies for accomplishing this. One is probably something you have already seen or heard of, and I've even hinted about this before. So essentially it means that first synthesize everything in the normalized frequency domain by doing your low-pass prototype response. Find out the coupling matrix in this domain, as we have actually seen so far. And finally, once you have your S21 and S11, apply the desired frequency transformation from the normalized low-pass domain to a band-pass, band-stop, or any other thing that you have to basically get the true S21 and S11 as a function of frequency. The second technique is slightly different in the sense that we are basically starting already with the transfer function with a desired response and not with an equivalent low-pass response. That is actually a key difference, because once you start with a desired response, then you actually have to get a different transformation, because you're not transforming anymore from the low pass to a band pass or from a low pass to a band stop, but you're actually starting from a desired response. I know it's a little bit murky right now when we talk about generalities, but we will see actually both methods and you will see exactly the difference. So let me start basically with method 1, and this is essentially an outline, which is an outline we have discussed before, so I'm going to go very quickly. So once again, the key thing to remember here is we're starting from a normalized low-pass prototype. We're finding the S parameters from there, and then finally there is a frequency transformation that will yield the true S21 and the S11. So let me show you a few of these transformations so you get a good idea of how things look like. Some of those transformations actually exist in textbooks, some of those don't, and I want to show you both of them. So here's essentially what we are doing. This is the normalized frequency domain. This is the case where basically my cutoff is at omega is equal to 1, and I have both negative and positive frequencies. This is the real response that I want. In this particular case, for example, I want a fourth-order Chebyshev bandpass filter with a 0.1 dB ripple centered essentially around 2 gigahertz with a bandwidth of 100 megahertz. So if you basically go ahead and plot what I said in words in a graph, you could basically see the response here. So obviously to walk from here to there, you basically need some type of a frequency transformation. So the frequency transformation for a band pass is actually the one shown right here. And this is actually something you can find in several books. But I do want to kind of warn you a little bit that this is not a linear transformation. So if you actually look at this green curve right here, you realize that this is not exactly a line, but it's approximately a line if your bandwidth is pretty narrow. And in this case, it's actually pretty narrow. It's 100 megahertz at the center frequency of 2. And if in case that you're doing that, you can basically use this approximation down here, which is a linear approximation. Here's another example of how you can go from the same type of initially synthesized low-pass response to now a band stop, which is shown right here. Now notice that the S21 here is actually shown in blue, which means you basically need a notch in this case. And in this particular case, we will do the same thing. It's a fourth-order Chebyshev centered at 2 gigahertz. So the low-pass to band-stop transformation mapping is the one shown right here, which once again, and now it's more clear from the picture, it's a nonlinear transformation. So you need to be aware of that. Here's another transformation from low-pass to high-pass. And this is a transformation we've seen before. So here's basically the transformation that we need. Now here's an example that is a little bit more involved in the sense that I want to synthesize a dual passband filter. So when we're talking about a dual passband filter, it means I need two passbands. So here's an example. This is what I really want. I really want basically a bandpass filter with two passbands. And essentially, I still have to start from this low-pass equivalent prototype. So people have searched for equivalent frequency mappings, and here's basically the equivalent frequency mapping that you have to go from the normalized domain to the double bandpass domain. And by appropriately choosing, for example, the fractional bandwidth in each band, so here you have 2 bands, obviously, and 2 center frequencies, obviously, you can essentially successfully map the original response to pretty much any bandwidth you like for each band and any center frequency you like for each band. So it's a very powerful transformation that you can utilize. Here's the same thing, but now in the stop band domain. And again, this is something that you will not easily find in textbooks, but the similar idea works when you try to map the original low-pass response to now a stop band response, but now you actually have 2 stop bands. So very similar idea basically holds here. Now, let me give you a few remarks that I think you should be aware of as you basically work through these transformations. So the first remark I'd like to make is that in this methodology, when we start synthesizing our low-pass response in the omega is equal to 1 domain, we will always have some type of a coupling network in mind or a filter topology in mind, which will look like the one you see there with the red arrow. When you basically do the frequency transformation, that actually loses its meaning, because the true coupling topology that you will physically implement will not actually look something like this, right? This is essentially a mathematical technique that allows you to get the real response from a synthesized response, but the real filter that you will build will not look like that. In fact, the real filter that you will build, if let's say we are transforming things from low pass to band stop, it will actually look something that you see down there. And I'm going to spend a little bit more time explaining this diagram, but let me also show you the same thing for the case of a dual passband. So in a dual passband, we started from this coupling diagram, and basically we will implement something that looks like this. So the first fairly confusing thing here is that, yeah, we do all of these frequency transformations, but you're not building what you started with. Now, let's spend a little bit more time on these diagrams. What do they include here? So first of all, they include resonators. So same thing as they included before. But they also include another thing, which is here shown as NRN, or non-resonating node. So this is a concept which we'll discuss more in the second methodology. And honestly, we don't have time in this class to cover all the details of non-resonating nodes. But the easiest way that I can describe a non-resonating node right now is to basically say that this is essentially a connection point. So as its name says, node 3 here is non-resonating. So it's just a connection point. So at most, it will be something like a capacitor, an inductor, or something of this nature. So physically, you will see non-resonator nodes more or less like as LCs. They will not actually be resonators. So as you look at this coupling diagram, it's also important to realize why does this thing implement a second order band stop function. So let's try to explain this. So you have this guy right here, which when it resonates is an LC resonator that basically introduces an open, right? So this resonator rejects as an open. So at resonance, this thing is an open circuit. You have this coupling section here that basically introduces a phase shift beta L of 90 degrees. Remember, we talked about inverters having a phase shift of plus or minus 90 degrees. So if you go back to the Smith chart and you bring that in your mind and you look at an open 90 degrees away, the Smith chart is 2 beta L, so that means you're going to transform this thing at 180 degrees. Guess what? You go from an open to a short. So that means that the signal right here will actually see a short. Exactly the same thing will happen from the second resonator. So an initial open response at resonance through this inverter of 90 degrees will actually be translated now to a second short. So as you can imagine now, as the RF signal is propagating from the source to the load, it will face a reflection here. So here's your first band stop object, hurdle, let's say, and whatever little leakage you might have will actually face another response from here. So the best way to essentially understand those coupling diagrams is basically with exactly what I gave you here. By essentially thinking of what the response of this resonator is, how it's reflected from the coupling sections, and basically go from there. Similarly, you can interpret the coupling diagram here. Here, basically, each one of these resonators will undergo essentially 2 reflections until it basically goes to the signal path, right? So essentially, this will implement a passband response. Now, you might say, OK, I understand how this thing works if you give me the coupling diagram. But what would happen if I wanted to synthesize that response? How would I actually come up with this coupling diagram? So the answer to that is called experience and luck, right? So the answer to that is you read as many papers as you want, as you can. You see how many transfer functions have been implemented before, what coupling diagrams work for different transfer functions, and then you choose one of them for what you want to do. And of course, then ingenuity and innovation come, right? So because what you're trying to do is not really what anybody else has done, but again, with experience and with intuition and innovation, you can modify this coupling diagram to get what you want. So that's why it's called synthesis and not analysis. There are essentially multiple solutions that will basically yield the same thing. So in fact, the method 2, which we will start seeing basically from next time, does exactly that. The method 2 basically starts synthesizing a filter from this point on here. Oops. From this point on. So you choose the topology, and then you synthesize the filter, rather than choosing a low-pass topology and then scaling things. Right? So these are basically the 2 different approaches that we're talking about here. There are a couple of other additional remarks which I kind of already mentioned. So the first one is that the coupling matrix diagram loses its meaning when you transform from a low-pass to high-pass or anything else. So again, you don't implement what you see in the low-pass diagram. And finally, not every single characteristic that you might want can actually be implemented by the mappings that I gave you before, right? So for example, if you want an equiripple stop band characteristic, it's not going to happen from the mappings I gave you before. So you need to be careful of what characteristics of the filtering are critical and which ones are not.